Uttam Prabha. Digital India. Educated India.
Dear students, I welcome you all in the 7th lecture on crystallography. In this lecture, I will discuss about the nomenclature of crystal phase and crystallographic direction, and I will discuss the concepts of Miller indices, crystal zones, zone axis, and I will make certain simple calculations, so that you will be able to appreciate how these names of crystal phases and crystallographic zones can be done by yourself. So, let us first discuss about how this crystal phase nomenclature came into being. In the earlier studies, the crystal phases were named in the form of a parameter called Weiss parameter. Weiss parameter, this represents relative number of units at which a phase cuts each axis. It gives you an approximate indication of a phase's angular attitude with respect to the crystallographic axis, and the general symbol of this kind of Weiss parameter that was used to name a particular crystal is in the form of a say 2A colon 2B colon 1C. What does it represent? It represents that if in the C crystallographic axis, if there is a particular unit along which this phase has intersected, then along A and B crystallographic axis, twice of that unit that has been intersected here. Now, let us discuss how this particular Weiss parameter was initially done. To do this, one needs to think of a unit phase, which is also called a parametral plane. In crystallography, a unit phase or a parametral plane is considered as that phase which has the largest area, and it has been assumed that unit phase has a Weiss parameter symbol is 1A is to 1B is to 1C, and these are the intercept proportions along A, B and C crystallographic axis, that is in 1:1:1 ratio. But if you talk about the total intercepts, and if along each unit cell the intercept distance is unit cell length is A 0, along B is B 0 and along C if it is C 0, the total length is along A axis will be N A 0 amount, along B direction it will be N B 0 amount, and along C direction it will be N C 0 amount. Let us consider how to develop a Weiss parameter symbol of a second phase, if we consider one of the phase as the unit phase here or the parametral plane here. Let us consider this crystal here. There are two phases here. One, this particular one here, this is called the P phase, which has a larger area, whereas this phase which is called AS, this has a relatively smaller area. Both the phases have intersected the positive direction of A axis, the positive direction of B axis and the positive direction of the C axis here. And let us consider along A crystallographic axis, the intersection distance in terms of centimeter is 7.08, along B this is 8.70 and along C this is say 16.57. Whereas, this smaller phase S that has intersected the A axis at a distance of 14.95 centimeter, B at 18.34 centimeter and along C this is at 11.65 centimeter. What I have to do to calculate the Weiss parameter of the phase A is where you have considered the P phase at the parametral plane, then what you have to do is that the intercepts along A, B and C direction for the S phase has to be divided by the intercept amount in the parametral phase, that is here the P phase here. So, what you have to do? You have to divide 14.95 divided by 7.08 here, and for this along the B axis you will have 18.34 divided by 8.70, and along the C direction. So, you have 11.65, this is the intercept amount, it will be divided by 16.57. So, after the division you have a value in terms of fraction, that 2.111 along A, 2.108 along B and 0.703 along C. So, amongst this the smallest value is 0.703. So, what you can do is that you can normalize these values by dividing with the value which is the smallest value here, that is 0.703 here. So, this has been done here. So, this is 2.11 by 0.703, and after division here and you make it the values, the result you make it nearest whole numbers, and ultimately it gives this particular shape here 3A. So, along A axis the intercept is 3 unit, along B direction the intercept is 3 times, and along C this is the intercept is 1 time. So, essentially it tells you that the inclination of this phase is in such a way that you have that along A and B axis the intercept is 3 times the distance of intercept along the C crystallographic axis. In crystallography there is another issue that needs to be learned. We call this as axial elements here. So, in axial elements there are 2 terms we need to know. One is the interaxial angles. So, this we are already defined, the angles between the axis, we call it as interaxial angles, and the other is called axial ratio here. So, in axial ratio what happens here is that along the A, B and C crystallographic axis, if you have the unit cell length is A 0, B 0 and C 0, then if you normalize this unit cell length by the unit cell length of the B axis. So, you divide A 0 by B 0 and also B 0 by B 0, and also for here the C 0 by B 0. What you have here? You have a ratio here. What is this ratio? You have this ratio here is that A 0 by B 0 is to 1 is to C 0 by B 0. So, what you have here in this particular case here, if you talk about the phase P. So, if this is the unit cell length. So, if you have this particular one here 870 as the B crystallographic intercept. So, you divide this by this 8.70 and you get a value here which is 0.814 is to 1 is to 1.905 here. So, that means along A and C direction you have a ratio which is not equal to 1, and particularly for crystals belonging to triclinic, monoclinic and orthorhombic crystal system, you have this kind of values here, where along A 0 by B 0 is not equal to 1 and C 0 by B 0, C 0 by B 0 will not be equal to 1 here. But in case of isometric crystal system, you now know this axial ratio will be 1 is to 1 is to 1. Now, after that this West parameter symbol has been revised and a much simpler nomenclature has been devised and it is called Miller indices symbol. So, what you have to do? You have to have a crystal phase if this West parameter symbol is known. Say this is the West parameter symbol and it is written in this way that, and along the a axis this whole number has to be written, this is 3 a colon, and then along the b axis the whole number is to be written 3 b and colon, and then you have to write this 1 c here. So, if you want to convert this West parameter into Miller indices symbol, what you have to do? You have to take a reciprocal of these whole numbers here. So, 3 becomes 1 by 3, 3 becomes 1 by 3 and 1 is 1 by 1. So, in order to clear the fractions, you have to have an LCM. So, here this is 3 and you multiply the numerator with 3 here. So, you have here is that 3 by 3 1, 3 by 3 1 and 3 by 1, this is 3 here. So, you have up to this stage as comma and then you remove this comma and put 1, 1 and 3 under first bracket here. When you put under first bracket, this we call it as the Miller index symbol here, and this is the symbol of a crystal phase here. Now, this is an example of the Miller index symbol of crystal phases here, and you see these are the 3 crystallographic axes A, B and C, and the Miller index symbol of different phases have been given a name 111, 113 and say 1 bar 13. So, this was the P phase. If you go back and just see, this is the crystal here. This is the unit phase that we have talked about. That is why this unit phase has this particular symbol here 111 and this 113 that has been just we have converted the West parameter symbol into 113 here. So, what you have here is that apart from that, you see some symbols has been given a name 1 and then this is 1 is written and on top of it there is a bar symbol is there and this is written as 3 here. We pronounce it as 1 bar 13. When we write a bar symbol with a particular axis position here, it means that particular phase intersects the negative direction corresponding to that axis here. In this case, this intersects the negative direction of the B crystallographic axis, but it intersects all the positive directions of A crystallographic axis and C crystallographic axis here. You also have a situation here, in this case 1 1 1, it has intersected all the positive directions of A, B and C at unit cell proportion or unit cell length proportions here. When we have 1 1 bar 1, in that situation bar 1 is in the position of the C crystallographic axis. It means that is intersected the negative direction of the C crystallographic axis, but it is intersected the positive direction of A crystallographic axis and it has intersect the positive direction of the B crystallographic axis. So, this nomenclature we will be following in course of further study of the crystal phases here. So, let us have a further look here. Let us talk about a cubic crystal and you see that how the Miller index symbol and the West parameter can be linked and how the Miller index symbol is very easy to remember and particularly the inclination of a phase with respect to a particular axis, it is much easy to understand. Let us consider this particular plane here. This is your A crystallographic axis, this is your B crystallographic axis and this is your C crystallographic axis. What you see? This axis has intersected only the A crystallographic axis, but it is parallel to the B crystallographic axis and the C crystallographic axis. In case of isometric system, we call it as A1, we call it A2 and A3. So, theoretically if we talk about the waist parameter symbol here. So, along A, if we call that this is 1 unit length, it has intersected, let us say write 1, but it is parallel to B A 2 and parallel to A 3. That means, if it is parallel, that it is intersecting at infinity, at infinite distance here. So, that is why we write it for the B position as infinity here. So, if we take a reciprocal here, so this place is becomes 1 by infinity, 1 by infinity. So, that becomes 0. So, what it has become now, that this particular phase which is parallel to B and C or A 2 and A 3, that position will be now occurring as 0. So, the Miller index symbol, if we now remove this comma and we put under first bracket, then this phase will have a Miller index symbol of 1 0 0. Let us come to this particular place here. So, this is a plane which is intersecting this A 1 direction, it has intersecting this A 2 direction, but it is parallel to the vertical A 3 direction here. So, you write it that it is 1 unit, 1 unit. So, this is 1 1 and this is infinity along the C crystallographic axis. So, ultimately it is converted into a symbol, this is 1 1 0. Whereas, this plane here, this intersects A 1, A 2 and A 3 and equal lengths. So, that is all the parameter is 1. So, you have the Miller index symbol of such a crystal face, we call it as 1 1 1. Now, this can be further understood if we talk about this 3-dimensional crystal and where a variety of faces are there. So, what you have here is that if you talk about this face here, as I already told you, this face is perpendicular to the A crystallographic axis, that is intersected the A crystallographic axis. So, this is this plane here parallel to B and parallel to C. So, immediately in the position of B and C, there will be 0. So, 0 essentially refers to that it is parallel to those crystallographic axes. So, this is 1 0 0, it is parallel to the two crystallographic axis. Here this is intersects B, this is intersects A, but it is parallel to the C crystallographic axis. So, in the position of C, this will be 0 symbol here. So, it will have, if it intersects the unit distance in along A and unit distance along B, we call it as 1 1 0. What will be this face here? This face is parallel to A, this is parallel to C, but intersects the position of B. So, we call it as 0 should be in the position of A, 0 should be position of C, we will call it as 0 1 0. What will be this face here? This face is parallel to B, this face is parallel to E, but it is intersected the C crystallographic axis. So, there will be 0 and 0 in the position of A and B, and that is why it will have a nomenclature of 0 0 1. And this is the one, if you have the intercept in such a way that it has intersected all the positive directions of A, B, C, and the inclination is such that it is not it has not intersected A, B and C at the same distance here, and particularly the intercept along the C crystallographic axis is half the distance that has intersected along A and B. Then we have this symbol here is 1 1 2. And if this is talk about this face here, this is the face which is intersected the negative direction of B, but the positive direction of A, but it is parallel to the vertical C crystallographic axis. So, its nomenclature will be in the position of C there will be 0, and for the position of A it will be as usual 1, but since it is intersecting the negative direction, to show the negative direction we put a bar on this 1 here, which is lies in the position of B. So, 1 bar 1 0 will be this particular one here. Okay. So, with this understanding, let us have a look here that we have with this general symbol, the HKL symbol, that we have done it, the Miller index symbol that we have applicable for, say, for example, triclinic, monoclinic and say orthorhombic and then tetragonal, and say in isometric crystal system. In this 5 crystal systems, you have 3 crystallographic axes. So, you have an HKL general symbol of the Miller indices we know about. But we have, in case of hexagonal and trigonal crystal system, there are 4 crystallographic axes. So, theoretically there are 4 intercepts possible here. That is why you have a symbol, we call it as HKIL. So, this is called Miller-Brave indices here. So, H essentially corresponds to the intercept along the A1 direction, K this is A2 direction, and I this is A3 direction, and L corresponds to the C direction here. Now, one of the most important aspects here is that since there are 3 crystallographic axes, any intercept, any inclined surface, when it is intersecting the 3 horizontal axes, it cannot intersect all the 3 positive directions here. There will be at least one negative direction that has to be considered here. Because of this restriction, there is this particular part is maintained here, that is H plus K plus I is this condition is satisfied, H plus K plus I is equal to 0. Any symbol, if you have H K I L, then H plus K plus I should be 0 for a hexagonal or trigonal crystal system here. So, this is shown very nicely here with this diagram here. So, let us consider this particular phase here. This phase, if you see, it has this phase here, this has intersected the positive direction of A1, but it is parallel to the A2 direction, and it is also parallel to the vertical C crystallographic axis. So, we are not interested with the C intercept here, we are essentially interested to know this phase's intercept relationship with the 3 horizontal axes A1, A2 and A3. So, what you have here, this phase has intersected this direction here. This direction, this is the A3 axis here, from the center to this direction, this is the positive direction of A3, this will be the negative direction of A3. So, it has intersected the negative direction of A3, it has intersected the positive direction of, say, for example, A1, and it is parallel to the A2 axis here. So, what you have here, if this distance is the same, you can write it as 1, 0 has to be there in the position of A2 axis, and you have to put a bar 1 for the position of A3 crystallographic axis. And if you see this, if you add 1 plus 0 minus 1 is equal to 0, which we have just learned that H plus K plus L, H plus K plus I, that will be 0 here. Let us consider this phase here. This phase has intersected the A1 direction, has now intersected the A2 direction, but it has intersected the negative direction of A3, something like this. So, in this case, if you consider the intercept and convert it into Miller index symbol, so this will be this symbol here. So, 1, 1, bar 2, 0. So, even if you add it up, you will have 1 plus 1 minus 2, this is 0 here. And if you have a situation where you have a triangular, this is this phase here, which is intersecting the positive direction of C crystallographic axis, and it has also intercepted this 3 horizontal direction here, something like that. So, you also have 1 1 bar 2 1. So, you have a situation, this is if you add this up 1 plus 1 minus 2, this is 0 here. Let us study what is the geometric relationship which allows this particular condition to be satisfied, that is h plus k plus I is equal to 0. To do that, let us make very simple calculation here. Let us consider a face that has intersected the 3 horizontal axes here, A1, A2 and A3. So, this axis position has been shown here. So, this is the negative direction of A3, this is the positive direction of A1 and this is the positive direction of A2. Let us consider that this face has intersected the positive direction of A1 at point M, the positive direction of A2 at point T and the negative direction of A3 axis at point X. And if A0 is the unit cell length for all these 3 axes here, then this will be, this OM is equal to, let us consider that M times A0. So, this is M A0, this becomes OT is equal to N A0 and OX, let us consider this is equal to X into A0. And we also know that the angle OM with that makes with OT, this is 120 degree and the A3 direction, this bisects A1 and A2. So, this angle OMX, this MOX, this angle is 60 degree and TOX, this angle is 60 degree. If we have this broad idea, then let us make an equality here. What is this equality? The area of the triangle OMT can be divided into 2 sub parts. One part is that OMX triangle and the OTX triangle here. The total area then of OMT will be equal to the area of OMX plus the area of OTX. We can make the, we can determine the area of any triangle if you know the length of the side, length of 2 sides here and also the angle between these 2 sides here. If you know that, it will be possible for us to determine the area. How? Using a formula. What is that? Half into the multiplication of lengths of the 2 sides and the sine of the angle between the 2. If we do that, then what will be the area of this triangle OMT? This will be half into this distance OM that we have written as MA0 into this distance OT, which we write it as NA0 and the angle between these two is 120 degree. We have to take the sine value. So, this becomes sine 120 degree. This equals to the area of this triangle OMX. So, this is half into MA0, that is this distance OM, and then we multiply this distance, that is OX. So, we have XA0 and this angle is 60 degree now, we write it as sine 60 degree plus the area of this triangle OTX. So, OT, this is NA0, OX, this is XA0. So, it becomes half into NA0 into XA0 into sine 60 degree. And you also know that sine 120, you can write it as sine 180 minus 60 degree. That means, that is becomes sine 60 degree. So, you can have on either side of the equality, in the denominator you have 2, you have in the numerator sine 60 degree and you also have common A0 square. So, if you eliminate that and you can make this and you can make x in one side, then x becomes m n divided by m plus n. What is, how you can relate it with m with the Miller-Brave indices, that is h k I. So, you know that the intercept and the Miller index integer, they are related to each other by reciprocal value here. So, if you have h, then h is equal to 1 by n, and if you have k corresponding to A 2. So, k is equal to 1 by n, and if you have I that corresponds to the A 3 axis. So, I will be 1 by x, but since it is in the negative direction of A 3, we put a negative sign here. So, what we have here is that I is equal to minus 1 by x. So, if I put the value of x here, that is what is that? X is equal to m n divided by m plus n. So, x is in the denominator. So, then it becomes minus m plus n divided by m n. So, now you have, if you multiply with m n, so what it becomes? So, if you have to, if we clear the fraction, so what you multiply with? You multiply with m n. So, in the h is equal to, it becomes n, k becomes m, and in this case it becomes minus m plus n, I becomes minus m plus n. Now, if you add it up, h plus k plus I, so it becomes n plus m minus n is equal to 0. So, we prove that h plus k plus I is equal to 0. So, with this very simple geometrical proof, in case of a Bravais-Miller indices, the 3 integers corresponding to the 3 horizontal axes A 1, A 2 and A 3, that integers always have to add up and will become 0. If there is a non-zero value, immediately you know there must be some problems in calculations. Okay. So, let us now how to assign these Miller indices here. So, if you have faces that cut only one axis, that means you have 2 0 position here. So, 1 0 0, 0 1 0 or 0 0 1. If there are faces that cut 2 axes here, that will be only 1 0 position, there will be only 1 0 in the Miller indices. So, it will be either 1 1 0 or 1 0 1 or 0 1 1. Those faces that cut 3 axes, we call it as 1 1 1. This is called a unit face here. Okay. Let us now understand the concept of crystallographic direction, crystallographic zone and zone axis. Let us make some simple definition and then we make some simple calculations here. So, how to give a name to a particular direction? So, you remember that when we name a particular face, we have given this symbol H K L. H K L, if we talk about Miller index symbol. So, H K L under first bracket, that is a face. For a direction, generally we use this terminology U, V and W. U corresponds to the A axis, the V corresponds to B axis and C corresponds, W corresponds to the C axis, and they should be put under the third bracket here. So, any direction with this symbol is essentially, it refers to the components along the 3 crystallographic axes. It is very nicely shown here. If this is a direction which we tell it as U V W, then if we draw a perpendicular from this point to this horizontal plane here and it intersects at this point, and if there are 2 parallel lines are drawn parallel to this axis, that is this line, and parallel to this axis, this line here, then this will be the coordinate u will be this coordinate here or this distance here from the origin, whereas v will be this distance here along the b axis here, whether and this direction, this distance is w along the c crystallographic axis. So, this is the nomenclature of any direction under a symbol of UVW. Let us now discuss this in some more details using a two dimensional lattice here. So, where you see these are the lattice points, they are oriented or translated along this direction. Let us consider that is B direction, and let us consider that this is A direction here. So, we are not considering the third direction here, that is C crystallographic axis. One thing immediately you can note that this distance A and this distance B, they are unequal. So, A is not equal to B. So, that is very important here. Now, you see any direction. So, let us consider a direction that passes through this lattice nodes here. If this is the origin, what is the coordinate of this point? So, this point, if we talk about this distance here, that is the distance along B, and this is the distance along A. So, this is the unit cell dimension along B, this is the unit cell dimension along A. So, I will call it, this coordinate will be 1 1. So, if we are here, so this is the twice this distance along B, this is the twice along this. So, this will be 2 2. So, any direction that passes through these coordinates here, you will have 1 1 0, because it is parallel to the vertical axis here. So, this is not, the intercept is not there along the C axis, and what you have here, there is 0 intercept along the C axis. So, it is essentially lying on this horizontal plane. So, it will be theoretically it will be, the symbol of this line will be 2 2 0, it will be 3 3 0, but we take the smallest value of the integer. So, this line will have a value of, or will be symbol of 1 1 0 under the third bracket here. If we talk about a line that passes through this point here, what is the coordinate? This coordinate is essentially 1 unit distance, and this is where this is 3 unit distance here. So, the coordinate of this point is 3 1. So, any line passes through this will be a symbol of 3 1 0. Now, let us consider this phase here. If this is the phase here, which is a phase which intersects the A axis and B axis as unit cell length. So, and it is parallel to the C crystallographic axis, that is why in the third position, that is 0 symbol here. So, this is 1 1 0. One interesting development here is that a line with the same symbol, with the phase the same symbol 1 1 0 and 1 1 0. This line in this particular case is not perpendicular to this phase. So, this is very important, that accepting the basal section of tetragonal, hexagonal, and also unless this is in isometric crystal system, this particular direction, a lattice direction, is not parallel to the normal to the plane indexed with the same integers. Say for example, plane is 1 1 0, direction is 1 1 0. In cases, say for example, for triclinic, orthorhombic, monoclinic, these will not be perpendicular to each other. Particularly if we are talking about and in case of hexagonal, tetragonal system, if we and trigonal system, if we talk about the basal section here, in this case this distance A 1 or A 2, they will be equal, or in that situation 1 1 0 will be perpendicular to the same, to the face with the same integers as the symbol of that face here. So, this is a very interesting part that you should remember, particularly crystals belonging to monoclinic, triclinic and orthorhombic crystal system. This will never be perpendicular to each other. The direction and the plane with the same integer names will not be perpendicular to each other. You can also think of the same nomenclature in the 3D lattice here. So, same terminology you can think of here. The third dimension you can think of here. So, you can think of the intercepts along any point on the line. So, you can put within the coordinate system. So, along the 3 directions through which intercept it is passing through. So, if it is passing through a direction where it is intersecting the negative direction of a particular crystal. So, for that direction you have to use a bar symbol as we have done it before. So, let us see in some details here. So, let us consider this particular plane here. We remember that we call this plane as 1 0 0, and in this particular case, if you see here this direction here, this direction is has only intersected this plane here, and along this point the b coordinate is 0, c coordinate is 0. So, obviously, the simplest nomenclature of this line will be 1 0 0. So, if this is a cubic crystal, then 1 0 0 will be perpendicular to the 1 0 0 crystal face here. If you think of this direction here, in that direction, if we are here at this point, what will be the coordinate along this axis? This will be this distance here, and along this axis this will be this distance. If this is of the same unit cell length, so then this coordinate will be 1 1, and since along this is c intercept is 0. So, it will be a nomenclature here, this is 1 1 0, and if it is a cubic system, and in that situation this face will have a nomenclature of 1 1 0, because this is parallel to the vertical C crystallographic axis. That is why in the position of C crystallographic axis you have 0 position here. So, in that situation also 1 1 0 direction will be perpendicular to the 1 1 0 plane. Then you have a direction like this, where at this point here you have a coordinate is 1 1 1. So, that is why the direction is called 1 1 1. And if you have this plane here which intersects all the 3 directions, this is an incline to all the 3 directions, but with equal intercepts along a 1, a 2 and a 3 axis. In that situation also, in the isometric crystal system, 1 1 1 direction will be perpendicular to the 1 1 1 plane. Now, let us come to the concept of zone axis. We now have an idea how to give a name to a particular direction. So, we can give a symbol to the zone axis. So, before that, let us understand what does it mean by a crystallographic zone or crystal zone here. Zone represents faces or planes in a crystal, and these faces are parallel, have parallel intersections. So, let us see this particular thing here. So, you see there is this plane and this plane here or this plane here, their intersection is this line. So, this intersection is all parallel to each other. So, all these 3 planes are parallel to this direction here. This common direction of intersection is given the name called zone axis here. I can give you further example with this crystal here. Let us consider this crystal face here. This crystal face has a Miller index symbol of 1 1 0. So, this is your A crystallographic axis, this is your B crystallographic axis, and this is your C crystallographic axis here. And when we write 1 1 0, it means that is parallel to the C crystallographic axis, and it is intersected the A and B direction at unit cell lengths here. Whereas, this plane here is also parallel to the vertical C crystallographic axis, but it had intersected the negative direction of the B axis here. That is why it has a name, this name is 1 bar 1 0. The intersection of this plane with this plane here is this line here, and this line is parallel to this line here. We can also think of the intersection of this line here 1 1 0 with this plane here. What is this plane? This plane is parallel to the C crystallographic axis. This plane is also parallel to the A crystallographic axis, and it has only intersected the B crystallographic axis. Since it is parallel to two directions, so there will be 2 0 here. 1 0 will be in the position of A crystallographic axis, and the other 0 will be in the position of C crystallographic axis. That is why it is a given in symbol of 0 1 0. So, 0 1 0 plane and 1 1 0 plane intersects along this line, which is also parallel to this line and which is also parallel to this line. That means, these three faces here 1 1 0, 0 1 0, 1 bar 1 0, and also the fourth face, which is the opposite to 0 1 0, that means 0 bar 1 0, they lie in one zone, and that direction, the zone axis, is this line here. And what will be the symbol of this line? Along this line, it is parallel to the C crystallographic axis, the coordinate corresponding to A direction and coordinate corresponding to B direction is 0. So, that is why it will have a symbol of 0 0 1. So, these four faces lie in a zone which is given by this 0 0 1 symbol. The zone axis symbol is 0 0 1. Okay. With this idea, let us further discuss this, that so what we have here is that in case of a zone symbol, there should be two planes which will be intersecting and a common line, that this line will be your zone axis. And if there are three planes, they can also intersect in a common line, and you can also have a zone axis here. And how to represent the zone axis here? So, if it is a symbol is u v w, and you can in vector nomenclature or vector symbol, you can write it u I plus v j plus w k. And in this kind of determinant symbol, you can write it as, if there are face symbols are h 1, k 1 and L 1. If there are two faces which are intersected, one face is h 1, k 1 and L 1, and the other face is h 2, k 2 and L 2. If they lie in a zone which is determined along that as A, B, C or I, J, K direction, then you can write within this symbol here, and you can calculate what is the value of I, the value of or the value of u corresponding to I, the value of v corresponding to j, and value of w corresponding to k. So, that I will show you shortly here. Now, one of the important thing in crystallography is that a particular face or a plane, if it lies in a particular zone, then there is a condition has to be met, and that condition is that if the plane or face has a Miller index symbol of h k l, and if it lies in a zone that is u v w, that the zone condition will be you multiply h with u, add it with k with v, and add it with L and w. So, you have this h u plus k v plus L w. If they add up to 0, then we can tell that a particular face lies in a particular zone here. The other important issue here is that if there are two faces here, they lie in the same zone, then we can use additive rule or subtractive rule to tell that h 1 plus k 1, h 1 plus h 2, k 1 plus k 2 and L1 plus L2, they also lie in the same zone here. And this particular one we will be applying at the later stages of the crystallographic class here. So, please remember this additive rule, and also you can same way you can write H 1 minus H 2, K 1 minus K 2 and also L 1 minus L 2. This particular thing you can they will also lie in the same zone, in the zone where H 1 K 1 L 1 and H 2 K 2 L 2 lies. Now, let us calculate this very simple calculation here is that let us consider that you have two phases here. So, you have this. So, 1 1 1 and 1 0 0. So, this is the one here. So, if you have 1 1 1 and 1 0 0, these are the two faces. What is the zone in which these two faces lie? So, what you have to do? So, you now know that you put this, take out this column and this row here, you multiply with 1 into 0 minus 0 into 1. So, this in the place of u, this will be 0 here. Then in the place of v, that is minus v. So, you take out this column here and this row here, this is 1 into 0 minus 1 into 1, that is minus 1. So, minus v is equal to minus 1. So, this v is equal to 1. So, we put it 1 here 0 1, and what will be the value of w? So, to calculate w, you will take out this column out and you take this row out here. So, 1 into 0 0 and minus 1 into 1 minus 1. So, you have here minus 1 here in the position of w. So, minus 1 will be shown by this bar symbol here. So, the direction here or the zone axis has a symbol of 0 1 bar 1, and this is the symbol, this is this particular line has a coordinate along this line. Everywhere your A intercept is 0. So, what you have here it is the negative direction of C crystallographic axis. When you are here, this is the minus 1 corresponding to the C crystallographic axis, and this is the direction. This is you have the intercept along the B crystallographic axis, and here you have the 0 intercept along the A axis. So, this is the line here. Now, the question here is that is this direction or zone axis lies in the same plane, or let us consider a plane which is called 0 1 1. So, is this plane lies in the zone with a symbol of 0 1 bar 1. So, let us apply this zone condition here. So, you have H u plus K v plus L w. Let us see whether this is 0. So, we multiply 0 with 0, 1 with this 1 here, 1 into 1, and 1 with minus 1 here, this is minus 1, if you add it up it is 0 here. So, immediately we know that this plane, this is the plane with a symbol of 0 1 1, and in that plane lies this zone axis which has the symbol 0 1 bar 1, and we know by using this zone condition that they lie in the same zone, the face lie in the same zone here. Apart from this, we need to learn two other important aspects here. One is the tautozonality of crystal faces. What is that? If there are 3 crystal faces H 1 K 1 L 1, H 2 K 2 L 2 and H 3 K 3 L 3, they will be considered tautozonal if they lie in the same zone. So, how will you know that? If we can calculate the determinant, if the determinant value is 0, then we will consider that these crystal faces are tautozonal. In a similar way, we can also consider coplanarity of direction in a crystal. What does it mean? That if there are 3 directions, with the symbol u1, v1 and w1, u2, v2 and w2 and u3, v3 and w3, they will be coplanar if they lie on the same plane here. And what is that? The determinant of this particular u1, v1, w1 and u2, v2, w2, if the determinant is 0, then we can consider that these three directions are coplanar, they lie in the same plane here. Okay. So, now let us make some simple calculations here. What is this calculation? So, let us calculate the zone axis for the planes 1 1 1 and 2 1 2, and we also calculate the plane that lies parallel to 3 0 bar 1 and 2 1 0. We also you can also calculate the Wess symbol for a phase which has Miller index of 1 to 0, and we also calculate the Miller index symbol for a phase with the Wess parameter 4a, 2b, 1c. So, these are 4 simple calculations that you can practice here. So, I give you the procedure here in the next slide here. So, let us start with the first one here. So, let us calculate the zone axis if two planes are given and they are told that they lie in a particular zone. And what is the zone axis symbol? So, you will write this particular determinant here and you calculate the value of u. So, how to calculate the value u? You take out this column out, you take this row out and then you cross multiplication it 2 into 1 minus 1. So, this value u value is 1 and minus v is equal to 2 into 1 minus 2 into 1. So, minus v is equal to 2 minus 2 is equal to 0, that is 0, v is equal to 0. And what will be the value of w? So, you take this column out and this column this row out. So, what happens? 1 minus 2. So, this is minus 1. So, the zone axis will have a symbol of 1 0 bar 1. Now, let us calculate the second problem. In the second problem, let us address this second problem here. So, what we have to do? We have to calculate the plane in which lies these two directions here 3 0 bar 1 and 2 1 0. We use the same thing here. So, now you will be calculating the phase, that is why you will be using the symbol h, k and l. And we have written these two directions here 3 0 bar 1 and 2 1 0 here. Now, you calculate h. So, 0 minus minus 1, 0 minus minus 1. So, this is 1 and minus k 3 into 0 0 and 2 into minus 1 minus 2. So, minus k is equal to minus minus 2, that is 2. So, k is equal to minus 2, whereas L is equal to 3 into 1 minus 2 into 0, that is 3. So, h, k and L will be 1 minus 2, 3. So, this will be the Miller index symbol of the plane in which lies these two directions here. What will be the Wess symbol for the phase 1 2 0? What you have to do? You have to first make the reciprocal of this integer. So, 1 by 1, 1 by 2 and for 0 1 by 8 we will make 1 by 0. So, if you want to take out the fraction here, so we will multiply with 2. So, we now have for the position of A, we now have 2 here 2 into 1 by 2 1 and 1 by 0 means infinity. So, the Wess parameter symbol of this phase will be 2 a, 1 b and infinity c here. Now, you calculate the Wess symbol for this phase which has a symbol of 1 to 0. We have to calculate the Wess parameter here, or okay, we have already done this. So, this fourth one is that we have to calculate the Miller index symbol for the phase whose Wess parameter is given as 4a, 2b, 1 c. Same way we have to make the reciprocal of these integers. 4 becomes 1 by 4, 2 becomes 1 by 2 and this is 1 by 1 and so the LCM is 4, you multiply with that. So, here 1 by 4 into 4 it becomes 1, 4 into 1 by 2 it becomes 2 and 4 into 1 by 1. So, this is 4. So, the Miller indices symbol will be 1, 2, 4. So, this 4 simple calculations can be taken up to address even more complex calculations that may have in this regarding the nomenclature of crystal phase and nomenclature of zone axis here. So, with this we come to an end to this lecture here. In this lecture I have given you an idea how a phase can be named and how a direction can be named, and we will find out at later stages here how this nomenclature will be very useful when we will be studying crystal forms here. Thank you. With this we end. So, we will meet in the next lecture. Thank you.